Hello, class. This is Mr. Hart. And in this podcast, we want to start our unit on waves, sound, and light. And we want to get into wave properties. Basically, how can we describe a wave, what is a wave, and what can we do with it? Okay, so let's just start with a simple question. What is a wave? Okay, when you hear the word wave, you probably think of like an ocean wave. Okay, usually involve water of some kind. That's the kind of wave we usually see. But there's a lot more important waves than just water. For example, sound is a wave that's constantly around us. This is what allows you to hear my voice through the speaker. Your speaker sends out a wave to your ears, which is what you hear. Okay. Light is a wave. That's how you are able to see. There's versions of light that we use for special things like radio waves and Bluetooth and all these things. So waves are constantly around us. So we probably should know what they are and how we represent them mathematically. Okay. So let's just get into what is a wave. To be very precise, a wave is the oscillation of particles or energy. Okay, you've often probably seen waves drawn like this where they go up and down and up and down. Okay, but think about it, that wave is constantly moving back and forth and back and forth. It's just an oscillation. Okay, it goes from one spot back to another. But as it does so, it propagates energy along. Okay. Now, a lot of waves, like sound, for example, have to have some type of substance that they travel through. This is what we call a medium. Okay, so the medium for sound is air. Okay, for water waves, it's obviously the water. Okay, so a lot of waves will need a medium to travel through. Okay, now light does not, but we'll get to that a little bit later. Okay, so the first day of the unit, we did a little inquiry lab on waves and describing them. And we talked about a lot of terms that we want to be able to describe for a wave. Okay, let's focus on a couple of big ones. Okay, for any given wave, there's different parts of the wave we can represent. There is the crest and trough. This is the top and bottom of the wave as it oscillates back and forth. There is the amplitude of the wave, which describes how large the wave is. Larger amplitude usually means there's more energy in the wave. And then wavelength describes how far away these troughs or crests are from each other. Okay, there's long, slow waves or really quick, fast oscillating waves. Okay, you'll see both in nature. So a couple of the terms you're going to want to be able to describe are the amplitude, which is the height of the wave from the center. Okay, it's related to how much energy there is. The wavelength is the distance between peaks of the wave. Again, describing if it's a long, slow wave or a short, fast wave. Okay, there's the frequency, which tells you how fast it goes back and forth for each individual particle. Okay, how long that takes to go back and forth. And then there's the period, which is the time for a single cycle to pass. Okay, and frequency and period are related, but we'll get to that in a second. But basically, we can describe how tall is the wave, how long is the wave, and how quickly is it moving back and forth. Okay, those are kind of the three things we need to describe any type of wave. Okay, how much energy do we have, how long does it take to propagate, or how long is that wavelength, and how quickly is it moving. Okay. All right, so I mentioned energy a lot so far. The thing I want you to understand is there's lots of things that contribute to the energy of a wave. An amplitude is the big one, but there's also a wavelength component to the energy. So one of the big ideas is that the energy of a wave is inversely proportional to the wavelength of the wave. Okay, and this can make sense if you think about sound, for example. Okay, if you think of a long wavelength, that's associated with a really low sound like a tuba or a bass, right? It takes a lot of energy to make that sound come out, and that's why people pay for really expensive subwoofers and stuff like that, because you need a lot of amplitude and a lot of energy to get the sound to come out well. But if you think of like a really high instrument like a violin or a flute or a piccolo, okay, that sound is really easy to hear, and it can hurt your eardrums a lot depending on the situation, because that sound already has a lot of energy because it's a short wavelength that is occurring. Okay, so those really short wavelengths can have a lot of energy associated with them. Okay, and so in other words, the way to think about it is a longer wavelength means lower energy, and a shorter wavelength means higher energy. Okay. We'll come back to this as well. Again, this is just a law of introduction of the different types of things we're going to want to analyze with the different types of waves. Okay. But one way to visualize this is if we have three waves of the same amplitude. Okay. The long wavelength, low frequency waves will have very low energy, and the medium frequency with the medium wavelength will have medium energy, and the really high frequency with the really short wavelength is going to have a lot of energy. Okay, so shorter wavelength usually means it's going back and forth faster as well. Okay, the longer wavelengths usually mean it's going back and forth slower as well. Okay, so the frequency just describes how quickly it goes up and down, up and down. Another relation you're going to want to know for the homework that you'll see a lot is what we call the frequency equation. Okay, the frequency of a wave is related inversely to the period of that wave. So this represents period, and this represents frequency. Okay, so frequency is just another way of describing how fast it's oscillating. It's the inverse of how long a single cycle takes. So one way you can think about it is the period tells you how many seconds it takes to complete a cycle, and the frequency is how many cycles it can do in a second. Okay, so they're just flipped. Okay, period is just measured in seconds. Frequency is measured in 1/seconds. Okay, this is what we often call hertz. Okay, named after a guy that analyzed waves a lot. Okay, so capital HZ, named after a guy named Hertz. This is what your radio and your like FM stations are measured in, is in megahertz. Okay, but again, it's just a way of describing cycles per second, whereas period is seconds per cycle. Okay, so relatively straightforward equation. You just inverse whatever you're given, and you get the other value. Okay. So let's do an example problem really quick. So a wave has a period of 0.06 seconds. What is the frequency of the wave? Well, we're given period, we want frequency, so we just need to invert or divide from 1 the value that we were given, and that will give us the frequency. Okay, so 1 divided by 0.06 gives us about 16.7 hertz. Okay, and that's relatively straightforward. You could also have the other value. If you have a frequency of 440 hertz, what is the period of the wave? Okay, so that means it's going up and down 440 times a second. Okay, this is actually concert A, by the way, for any of you that play instruments. Okay, so concert A. So yeah, the sound that's 440 hertz, that means that the wave's going back and forth 440 times in a second. What is the period? Well, again, we just invert it. So 1/440 hertz will give us seconds per cycle. Okay, and that will be about 0.0023 seconds. Okay, so that wave is moving so fast that it will go back and down, or up and down one time in 0.0023 seconds. Okay, now I know this is kind of a lot to just throw at you right away when you're just learning about waves, but I want you to understand this so that you can easily switch back and forth between the ways they describe waves. Okay, you'll see some people describe waves in terms of frequency. You'll see some people describe in terms of period. It just depends on kind of the textbook or whoever you're talking to or whatever the context is. Okay, but you should be able to switch back and forth between these pretty quickly. So the two types of ways that a wave can propagate is it can be either a transverse wave or a longitudinal wave. Okay, so transverse wave is a wave that propagates perpendicular to its direction of travel. Or this is kind of the standard wave we usually think of a wave going up and down as it moves this way. Okay, but you can also have longitudinal waves, which are waves that compress as they go in the direction of travel. So they'll compress, move, okay? And so we can see this in this demonstration right here. Okay, so right here we have an example of a longitudinal wave. So if you look at this slinky, you can see, if you look closely, the compression that's occurring along the side. But when we have a transverse wave, it just goes up and down in the direction that it is propagating. Okay, so you probably have seen transverse a lot, longitudinal less often, but it is just a pushing back and forth, compressing of that wave. Okay, so transverse wave moves up and down as it moves to the right. Longitudinal wave moves with the wave itself. Okay, light is an example of a transverse wave, and sound is an example of a longitudinal wave. Okay, so going back to sound for a second, if you think about it, when I speak to you, the air particles that are coming out of my mouth compress the air particles that are nearby it. Okay, they hit into each other, and they hit into other particles and hit into other particles, and that wave propagates in the direction as I speak. Right, it goes with the direction of the wave. Okay, so it compresses things, and that's what generates the wave movement. Okay, so here's a illustration of the wave propagation. So for longitudinal waves, you can think of them piling up or compressing. Air particles are a great way of thinking about this, right? They just hit into each other. They compress, decompress, compress, decompress, kind of like an accordion as they move along. And then transverse waves just move up and down as they move, okay? They just oscillate as they move in that direction. All right, I know we've covered quite a lot of introductory terms, but there's one more thing I want to go over, and that's the wave velocity equation. So there's a way we can actually calculate how fast something is moving if it's a wave, and that is determined by, first of all, the velocity that we're looking for, the wave velocity, how fast the wave is moving, is determined by this guy is what we use to represent wavelength. Okay. And if you're wondering what the weird symbol is right there, this is called a lambda. Okay. It's a Greek letter that I don't remember what it correlates to, but it's a Greek letter, looks like an upside down Y, and this is what we use for wavelength. And then F is frequency. Okay. And that's our wave equation. So if we want to figure out how fast a wave is moving, we need to take how long the wave is and times it by how fast it's oscillating. Okay. And I don't have time right now, but in class we talk about how we can kind of just derive this from regular kinematic equations, which is kind of cool. But for now, just kind of accept it on my word that the wavelength is equal to, or the velocity is equal to the wavelength times the frequency. Okay. So let's look at an example problem really quick. Okay. So a wave with a frequency of 50 hertz has a wavelength of 7.2 meters. What is the velocity of that wave? Okay. So again, it's just a simple multiplication. The key here is understanding and identifying what is the wave, what is the frequency, what is the wavelength. Okay. So this guy right here is our frequency, 50 hertz. Tells us how quickly it's oscillating back and forth. This right here is our wavelength, or lambda. So our velocity is just lambda times f, or wavelength times frequency, which gives us 7.2 meters times 50 hertz. And when we calculate that, we should get that it's moving at 360 meters per second. Okay? So that's a pretty fast wave. Okay? It's traveling faster than the speed of sound. So again, it's just multiplying the wavelength and the frequency together. That gives us our wave velocity. Okay? All right. And then a couple last terms to make sure we got down is there's two types of waves. There's a mechanical wave and electromagnetic wave. Mechanical waves do need a medium to pass through. That sound's a good example of that. Water waves, anything like that. Whereas electromagnetic waves is basically light, Okay, anything that can just travel without needing a medium. Radio waves, infrared, visible light, ultraviolet. You've probably heard these terms before. They're all just versions of light or electromagnetic waves. Okay, but we'll get to this more. Again, hopefully I didn't overwhelm you too much with all the different terms for this lesson, but I just want to give you a foundation of all the different things we're going to discuss throughout the unit. And so just make sure you do the homework and just kind of go through the terms and make sure you got these down, and we'll be able to have some deeper conversations about what is going on with waves and why do they act the way they do. But we need kind of some foundation in what are the properties of waves. So again, just go back and review anything you need to from this lesson, and make sure you get these terms down. But let me know if you have any questions, and thank you for watching.